Hey, have you ever tried to bake a cake? You can't just throw things in a bowl, right? You need a recipe. You need a certain amount of flour, a specific number of eggs. Well, chemistry has its own recipe book, and it's called Stoichiometry. Today, we're going to crack that code. We're going to figure out exactly how chemists measure their ingredients for chemical reactions.
But, and here's the really tricky part. Imagine your recipe called for 1 million individual grains of sugar. I mean, you can't possibly count them all, right? Well, chemists face this exact problem every single day. Their ingredients, atoms and molecules, are so tiny they're completely invisible. So how on earth do they pull it off?
And this is the heart of the whole thing. Chemical reactions are incredibly picky. They need exact ratios of ingredients to work. A little too much of one thing or not nearly enough of another, and your whole experiment could just fizzle out. You really can't just wing it when you're working with something as small as an atom.
So to solve this, chemists came up with this brilliantly simple idea. They thought, okay, instead of counting individual atoms, let's just count them in massive groups. Think about it like buying eggs. You don't ask for 12 individual eggs, you ask for a dozen. Well, chemists needed their own special dozen for atoms. And that, my friends, is where the mole comes in.
A mole is just a number. That's it. But it's a very specific, almost ridiculously large number, 6.022 times 10 to the 23rd power. So whether you're talking about atoms or molecules or whatever, 1 mole of that thing always means you have this exact number of particles. It is the chemist's ultimate dozen.
I mean, just look at that number. That's Avogadro's constant, and it is absolutely massive. We are talking 602.2 sextillion. It's a number so huge it's honestly kind of hard to wrap your head around, but it is the perfect size for counting atoms on a scale that we can actually work with in a lab.
Okay, so here's the crucial part. Even with this special counting number, we're right back where we started. You can't physically count out 602 sextillion particles. It's impossible. And this is where chemists got really clever. They came up with a workaround. You don't count them, you weigh them. But to do that, you need a totally reliable way to connect the number of particles, our mole, to a weight you can measure on a scale, in grams. That connection, that bridge, is called molar mass. Let's dig into how it works.
Molar mass is exactly what it sounds like. It's the mass of one single mole of a substance. It's the unique weight for that giant dozen of particles. And this number, which you can find right there on the periodic table, is the magic key that lets us use a simple scale to measure out a mind-bogglingly precise number of atoms.
Let's look at some examples to make this real. 1 mole of carbon atoms. That weighs exactly 12 grams. 1 mole of water molecules. That's 18 grams. Every single substance has its own unique molar mass. And this is how we build that bridge from the invisible world of atoms to the very real, very physical world of a laboratory scale.
And here it is. This little triangle is your secret weapon. It's your roadmap for navigating between mass, moles, and molar mass. It shows you exactly how they're all connected. Say you want to find the number of moles. Just cover up moles with your finger, and what do you see? It's mass divided by molar mass. This thing is the essential tool you're going to use for every single one of these calculations.
All right, enough with the theory. The absolute best way to really get this stuff is to just do it. We're going to walk through 3 essential calculations together. So if you've got a calculator nearby, grab it and let's do this. Okay, problem number 1. Let's say we have 10 grams of oxygen gas, and we want to know how many moles that is. Now, we already know the molar mass of oxygen is 32 grams per mole. So, how do we solve this?
We use our trusty calculation triangle. We know the mass and we know the molar mass. Our formula is right there. Moles equals mass divided by molar mass. So we take our 10 grams, we divide it by 32 grams per mole, and boom, we get our answer, 0.3125 moles of oxygen. It really is that simple.
Nice work on that one. Let's try another. This time, we're going to start with moles, and we want to find the actual number of molecules. So we've got 2 moles of carbon dioxide. How many individual CO2 molecules is that?
For this one, we need to bring back our big number, Avogadro's constant. Just remember, a mole is just a count. So if we have 2 moles, we just multiply that by the number of particles in 1 mole. That's 2 times 6.022 times 10 to the 23rd, which gives us an incredible 1.2 times 10 to the 24th molecules. Whoa!
Okay, you ready? Time for the final boss. Let's put everything we've just learned together. This is a 2-step problem. We're starting with a specific number of molecules, and we need to find their total mass in grams. You have all the tools you need? We can do this.
Okay, step 1. We have to convert our number of particles back into our standard chemistry unit, the mole. So we divide our number of molecules by Avogadro's number, and that gives us exactly half a mole. Perfect. Now that we have moles, finding the mass is easy. We go back to our triangle. Mass equals moles times molar mass. So 0.5 moles times 2 grams per mole equals 1 gram. See? You just combined 2 different steps perfectly.
And there you have it. You've just nailed the fundamental calculations of stoichiometry. You now know how chemists bridge that incredible gap between the invisible world of atoms and the practical world of the lab. Let's just do a super quick recap of the key takeaways.
If you remember one thing from all of this, let it be this. The mole is what makes modern chemistry possible. It's the bridge. It lets us take a recipe written for atoms and actually follow it using grams on a scale. It's a game changer.
So just lock these three things in your brain. The mole, it's just a count. Molar mass, that's your bridge from the count to a weight you can measure. And the calculation triangle, that is your map for getting from one to the other.
Okay, now it's your turn to be the chemist. Here is your final challenge. How many individual atoms are in 5 grams of helium gas? You know, the stuff in balloons. The molar mass of helium is 4 grams per mole. Use the tools we've just covered, work through the steps, and drop your answer in the comments below. You got this!
Thanks so much for joining us for this explainer on stoichiometry. Go ahead and test your skills on that challenge problem, and we will see you in the next one.